Welcome everybody. My name's Paul King. I'm the Groovy lead for OCI, and I'm going to talk a bit about functional Groovy. So there's actually about an hour and 15 minutes worth of slides crammed in the slide deck. So there's two sections I'm actually going to pretty much skim right over. I've left them in there because if you want to go and look up some of the libraries in those particular sections, you can go and have a look. So bear with me if I just flick over a few slides in a few places. So the slide deck will have the all of the material there. Okay. So OCI are the home of Grails and a new framework they're working on called Micronaut, which both make heavy use of Groovy and do a lot of functional stuff. So if you want to know more about them, have a look at their website or come see me. So what are we going to do today? A little bit of an intro. So it turns out that Groovy's had functional programming all along. So we'll quickly look at some of those aspects. Then what I want to do is actually just take a step back and so, okay, well, we've got this functional capability. How should I really be using it? Groovy doesn't claim to be a purely functional language by any means, but it lets you certainly have high levels of functional style right throughout your code. And it lets you do many things that you would expect to have in any functional programming language. So let's get in and start. So what is functional programming? At its simplest sense, it's just a paradigm that emphasizes functions. Now, what does emphasizes mean? Well, we're going to come back. That's kind of what the second half of the talk is going to look at. What do we really mean when we say functional? It's not just the ability to write a function, but the way you typically want to use that capability is going to be important. Now, functional programming isn't new. I can do it in assembly language or C if I really try very hard. Java has had methods, and we can write static utility class methods. That's just like a function in some sense. We'll talk about what kind of methods might be considered pure functions and things later on, but we'll get to that. So you can do those kind of methods in Groovy as well. Java 8's added lambda expressions and method references and streams. So there's a whole lot more functional stuff in recent versions of Java, and Groovy can obviously leverage all of that as well. And Groovy's had first-class functional support with its closures all the way along. So we'll have a look at what a closure is very quickly, but it's just something that has parameters and code and returns things, and there's some other special caveats about the environment and thing that I'll come back to. But let's have a look at what a closure is. There's an example up the top there. I've got a variable declaration. My variable's called twice, and it's just equal to this bit of code. So if you've seen a lambda expression in Java, that's what a closure is, a very similar sort of thing. Groovy 3 supports the Java 8 lambda syntax. I won't be showing, I don't think I've got any examples of that in this slide deck, but you could do the Java syntax version of all of these as well if you wanted to. Now there's lots of variations. So the first example there, I've given a type to the argument to the closure, so int for num. I could decide not to give a type. There's examples down there. The triple one that we'll get to, I could not even bother declaring the closure, and there's a default closure name called IT. We'll see examples of that. But once I've declared that variable, what can I do with it? Well, in my code, I can use it as if I'd declared a method somewhere. Okay, so twice of 5 is 10, and so on. It's actually just a shorthand for .call in Groovy. That's an implementation detail, but it's good to know that that's what's happening under the covers. Okay. I can have closures with no arguments. So if I just put the arrow symbol with nothing on the left-hand side, there's no arguments to twice 10. If I just invoke it with no args, it'll be 20. And there's one without a type. So it's basically got an object type or duck typing. If you're using that within, if you're using a lot of these things within compile static, there'll be type inference going on as well. And it's all typed even in dynamic Groovy, but runtime checks. Yep, so there's multiple ways in which I could have declared that. So the last one, I'm using the default argument IT. Up the top, I've got a method, So you'd expect to see that in a Java class. You can do that in a Java class in Groovy, or you can just have it in a script. And in the second bit of code is actually making a method reference. So it's actually a method closure in Groovy. You can actually use, again in Groovy 3, you can use Java's method reference syntax as well. Okay, there's also, we've already seen it, even if you may not have realized it, but there's higher order functional support. So I can have here, I've got a method now that can take a closure as a parameter, and I can pass closures to other closures and so on and so forth. I've got an apply twice method. I can pass in an argument and a closure. I can call that closure with that argument and then call the closure again with the result of the first call, and so on and so forth. I can have default values for arguments. So here for quadruple here, I've got arg and I've got a default value of 2. So if you don't supply an argument, which is the no arg case down the bottom, it'll actually fill in that argument. If you do supply the argument, it'll obviously use that as the argument value. You can compose arguments, so there's both forward and backward composition. So if I take any two closures, or a closure and a method reference, or method closure, I can combine them forwards or backwards. I can do partial application. So if I've got a closure that takes a bunch of parameters, I can decide to fill in some of those parameters ahead of time. Okay. So if I've got 40 is quadruple curry 10. So I'm pre-supplying the argument to quadruple, being 10. Now if I call 40, it'll produce 40. And more examples of functions as higher order or first class citizens. I've got collections of closures, so collections of code, if you like, and can do various things with them. Some bit of map filter reduce style processing happening there. We'll see more examples of that later. Now, a closure is actually, it's not a pure function in the mathematical sense, and we'll talk more about this particular topic. It's actually a closure in functional programming. Closures are defined as something that takes arguments and returns a value, but also is aware of its context. So there are free variables that, if they're mentioned inside a closure, they're bound to the environment in which it's defined. So in this particular example here, check answer is a closure. So it's a bit of code that has a parameter, guess, and returns some result. It's actually a Boolean. The result's going to be a Boolean, whether this guess thing is equal to some answer, whatever that is. You might ask, where did the answer come from, and where did log come from? They're outside in the environment of that closure. Okay, so when we talk, I'm going to talk a bit more about pure functions, and this can be this makes things very, very powerful if you want it, but if you do this too much, you can start to have sort of code smells that make your code very hard to reason about, and a lot of the advantages for pure functions will go out the window. So in this case here, it's probably fine. Actually using a log variable that's not going to change and not going to be, yes, I'm modifying the state of the log, but I'm not really modifying any state of any consequent, any significant parts of my actual code. So I can still reason about this particular example. There will be other examples we'll look at where it might not be quite so easy to reason about. Now, we've mentioned closures. They're used right throughout Groovy. So they were in the very first version of Groovy, and they're used everywhere. There's builders, there's metaprogramming, there's various sorts of a whole bunch of map, reduce, filtered, iterator methods that have been there right from the beginning, and they've got closures all the way through. Okay. Just a quick thing on style before I actually take a step back and look at things, a few more fundamental things about functional programming. So what I want to do here is, this is a little example where I'm going to try to calculate all the primes and all the palindromes. Does everyone know what palindromes are? Yep, something that looks the same forward and backwards. Yep, so 1, 2, 3, 2, 1 would be a palindrome. Yep. So I'm going to look for the numbers. I'm going between 1 and 200, and I want to find all the prime ones. I want to find all the palindrome ones. There happens to be a nice test for primes. I don't need to calculate all the primes and then see if my prime is in that list. There's a nice little test I can do with factorial. It's fairly efficient. we're not worried about the details of that. What we want to do is write the code that's going to... So I've starting off with some empty lists, and we'll talk a bit more about style and mutating and things later on, but for now, just bear with me. We've got some empty lists here. I want to calculate what the values of those 3 lists should be. So if I've got my imperative hat on, I think of, okay, I'm going to have a loop. I'm going to go through the numbers from 100 to 200. I'm going to check if it's a prime, because we've already done the test methods up there, is prime and is palindrome. I'm going to check if it's a palindrome. Then I'm going to check if it's both, and I'll put that in the both list. Okay, so that's all well and good. Then I might sort of realise it's a little bit inefficient, and I'm in control here. I'm doing things imperatively. I can put my efficiency hat on, and I can see, well, what I'm going to do is... I guess I should have said, why is it inefficient? Because I'm calling is prime twice, and that, even though I've said this factorial test is reasonably efficient, it's not zero cost. So I'm calling it twice. Well, let's just not call it twice. So I'll save it away in a Boolean variable, and now I can just test that Boolean twice. That shouldn't be too bad. So I've got both. I can do a final test down there and store things in the both list. Right? Makes sense? So doing things imperatively, I'm in control. That's a good feeling. That's where I want to be. That's why I do things imperatively. None of this functional stuff for me. But let's have a look at what the functional one looks like. And here it is here, and that's much easier for me to understand what's going on. If I wanted to maintain this code, this is a much better place to be in, right? So the argument you might have at this point is, do I go for the efficient one or do I go for the functional one? Well, you don't have to make that choice, is what I want to say. Because in fact, there's usually nice ways to do things functionally that is going to be efficient. So in this case here, I can just get the intersection of those 2 lists, and I'll get an answer very efficiently. Okay, depends on how efficiently intersect is being implemented, but it's an example, the kind of thing that you could potentially do. And in fact, even if I do things in a functional way, there'll be ways to go to a lower level in the functional sense. So I can use an inject method here and carry along the lists, and we can argue about mutable style as well. I can do this with persistent lists and things, or I've just used Java's lists in this case. So it's there's ways to go down to the lower level approach, even being purely functional, is what I'm trying to say. So you don't have to make that choice. You don't have to give up efficiency. And if you're into Java 8 streams, you can do the same sort of thing. Some different, the way streams are implemented in Java, there's some different efficiency design trade-offs that have been had there, but you can do a similar sort of thing. Okay, so what I want to do now is just sort of step back and say, so we've got closures. We can do anything we want to do functionally. What should we be doing? Because I've shown you different styles of functional. I did sort of low-level functional and high-level functional. What are some of the things that you are typically trying to achieve when you're doing functional programming? Well, it's kind of a mixture of declarative style. I can do semi-declarative style in imperative languages. I can go use Prolog or something that's a declarative constraint sort of style language. But functional puts a big emphasis on that. Controlling side effects, that's a really big one. We'll come back to that. And managing mutability is another thing that you typically want to do. So just because I've got closures, I can have closures and mutate everywhere. I can have closures and not control my side effects. I can have closures and still write imperative stuff. So let's have a look at what you might be doing in sort of each of these areas. And I've kind of covered all the things in there. So yep, you're wanting to go towards more declarative and recursion instead of imperative and iteration, controlling your side effects. Now, for me, it's not, I don't necessarily need to have pure code everywhere, but if I can't distinguish where I've got the pure code and where I've got the impure code, that's when I've got the problem. Okay, so that's something that you might want to think about. Once you do have areas that you know are pure, then there's a whole lot of things there. It'll be easy to reason about, more reuse possibilities, memorization, concurrency, caching, lazy evaluation, all come into play. And referential integrity is something that kicks into play there, and we'll come back to that. Mutability, hopefully that's fairly straightforward, and again, we'll come back to that in more detail. So we're now going to sort of look at those different pillars and look at things you might be wanting to do in functional programming. This would be true of any language that you're using. I'm going to show you examples of doing it in Groovy, and it'll hopefully give you some food for thought. Now here I've got two closures I've defined. One I've called increment. Looks pretty simple. Takes an argument and returns the argument plus 1. And then I've got an increment with side effect. Hopefully not too big a guess of which of these is impure. So this takes an argument and increments some x, which is some variable that's declared up there, and then it just returns the argument plus 1. So if we, are these both pure functions? Well, hopefully it's fairly obvious that the first one is, the second one isn't. So when I'm calling, I've got x and its value is going to be 4. I can call increment as many times as I like, and then I can always assert that x is going to remain 4. If I could start calling this increment with side effect, then I can't check that x is equal to 4 anymore. It'll be up to 6 if I've called it twice, right? So is this a bad thing? Well, we saw when we were doing the log scenario, sometimes it's not necessarily a bad thing, but there's often times when doing it in this particular style is going to make your code very confusing, and it's going to eliminate the ability to do some of the functional benefits that you get by having pure functions. So if basically I'm suggesting, even though I wouldn't say it's evil, it's going to be more difficult to reason about, and you need to understand the context. So if I've got a pure function, I just need to understand the input parameters, and the function definition will tell me what the output value is going to be. If I might have impure code, I've got to worry about the context. So is there any instant state? Is there any static state? Any global state? Is it mutating any of the parameters? Is it storing other global or static state? Is it going to throw an exception and all these sorts of things? So it's not necessarily evil, but there's a heck of a lot more that I have to reason about and think about if I don't do it that way. So I'm suggesting that for most of your code, you'd avoid the second particular style. Makes things much easier to reason about. Now, what we've just seen is kind of an example of what's called referential integrity. Okay, and so just to generalize what we saw on the previous slide, if I've got a closure that does something and I don't tell you what's inside it, if I see some sort of statements like what's down the bottom there, I've got x equals y plus 1 and z equals y plus 1, would I expect x and z to have the same value? Right? I'm assigning them the same expression in both cases. And if I've got do something in the middle of those two lines, would I expect this to execute successfully? If I know do something's pure, I can say yes. If I don't know if do something's pure, I have to go and look inside the definition of do something, which might be off in some other class or whatever in general. I've got to go and look inside it and see what it does. So I've got much, much more scope to what I have to reason about to handle this sort of scenario. Obviously, if do something is just going, if it is a pure function, it's just adding two arguments and returning them or whatever it might be, then everything will be fine. In fact, I can even do some slightly smelly things inside there, like I'm mutating one of the parameters, the default parameter into my closure. So it even might look slightly smelly, but it's actually only smelly inside that closure, and so that will still be okay. But if I start doing, because a closure is more powerful than a pure function, it can access its environment. If I start tweaking off to the environment, then this is going to fail. Okay, so I've gone and set y to 99. Obviously, the second z's going to be 100 now, and obviously this assertion will fail. So it's not that this is necessarily a bad thing. It's just that it's much, much harder to reason about. And there's another example with a list. If I go and do a mutating operation on a list, I'll have the same thing. We'll talk a bit more about immutable and persistent data structures later on, so we'll see ways to handle that. So going back to the sort of the general concept here, what referential transparency is if I see an expression anywhere in my code, if I've got pure functions everywhere, I can replace one expression with the other at any point in time. Okay, we can always substitute. Yep. Okay, and that lets us do all sorts of things. So we can calculate y plus 1 ahead of time. We can automatically do caching and concurrency and a whole bunch of other things. to give you, to sort of emphasize what you can actually do once you've got this sort of thing in place. We're calculating Pythagoras, using Pythagoras' theorem to calculate the length of a side of a triangle or whatever it might be. And I'm going to go x squared plus y squared and take the square root. If this is the bit of code that I've got and I'm compiling this, then because everything's a pure function everywhere, the Pythagorean method in this case is a pure function, it's not doing any side effects, then in fact, when the compiler analyzes this, and if this is the only place that in your code that uses it, and it's passing in constants into that algorithm, then at compile time, in fact, the compiler can actually go and calculate that and substitute for that whole expression. It can get rid of the method, and it can substitute the answer for that expression. And in fact, once it gets there, it can actually just say, yeah, assert true. It can say, and it'll do that at compile time. Okay, so you just have that constant being in your program. You can only do that kind of compiler optimization if you've got pure functions there. Okay, now Groovy doesn't do this sort of thing. Groovy's not in a state where it could, but just yet, well, it could do it in very simple cases for sure. And in fact, I could show you some code in a different talk that in fact does that for cases like this. But in general, it can't, because it can't tell whether you've got pure code there or not. So what I'm suggesting to you is to try to have pure code wherever you can, and if we add in more optimizations over time into Groovy, then you'll get those benefits. Now here's another, this is also an example of referential transparency, and it's sort of interacting with laziness. So here's a little bit of code that's, I've got some sort of stack of numbers. I'm going to pull things off the stack and calculate the power of one number by the other number. Okay, and so I'm going to pull them off in twos because I want something to the power of something. So I'm going to check that the size of this thing is divisible by 2, so that's a good check. And then what I'm going to do is walk through that stack, pulling off 2 numbers at a time. So I'm going s.pop, s.pop. And then I'm going to calculate the power of those. So I've got a little power function down the bottom here. Well, actually, I've got 2 definitions. This first one here is what you'd expect, base times exponent. And then I've kind of said, oh yeah, actually, I can do an optimization here. I know that if something to the exponent 0 is always going to be 1. So why bother even performing that calculation? It's inefficient. I can do a really quick check and have a nice little optimization in my algorithm there, and we'll come back and look at what the impact of that might be. Can anyone see anything in this code where referential transparency might become a question? Yeah, but so you're close, you're very close. So the issue is, this is an argument to the power method, and this is another argument. What order are these arguments evaluated in? Okay, Java and Groovy, it's always left to right. But that's an assumption that I'm making that's how it's going to happen. Okay, and here it's going to be fine, but if you don't realise that that's an assumption you're making, that can actually come up to bite you later on, and we'll have a look. So let's now, we've been told that laziness is a really good functional capability. So let's make a lazy version of this function here. And indeed, so lazy pop is just going to be a closure now. Right, so it's a closure that calls pop. And what we're going to do when the arguments come into power, it's actually going to call those closures instead of just using the parameters, okay? So this is all fine at this point, but now I go and add in my optimization. Remember how I had that optimization? Yeah, we'll go and add that in, and what happens? It blows up. Why did it blow up? Well, what happened was, if my optimization kicked in, I didn't actually go and pull these off. Okay, so I actually pulled off exponent on this side, but over here, I won't actually do base and exponent. And in fact, it's worse, because if the optimization doesn't kick in, I'm actually going to call exponent twice. So I've screwed up whichever way for this particular one, right? And this kind of subtlety, you might think, well, gosh, I've just been stupid and I've got stupid programming in here. But if you start using futures or you start using optional in Java 8, you've got this exact same problem. And you may not realize that that's what you're doing. So what referential integrity would tell you is don't do it that way. Well, this is, there's some more ways we can try to solve this as well that also muck up. So what I can do is to save that exponent thing being twice. There's other variations we can do here, which gets rid of 1/2 of the problems. But anyhow, we'll keep going. The way to solve it is to pull them both off and then just have your expression like that. Then you're fine. But what you really should prefer is not to ever go down that path in the first place. So in fact, let's not have a mutating stack. Let's actually have something that just uses index values. We'll leave the stack alone. We'll leave it immutable, and we'll just have an index that's walking along that stack, and we'll just pull things down. The thing is that the index never changes, right? So I just need to pull 0 and 1, 2 and 3, 4 and 5, and I'll be good. And I can do that in any order. My algorithm down here can change. I can do it in parallel, in reverse order. If I do these optimizations and I don't need to pull one of the numbers down, it doesn't affect the rest of the calculation. So what you should really be doing is using sort of immutable sort of structures and doing it this way. So there's just some things to think about. And again, if you've gone and used optional in Java 8 or something like that, this can come and bite you even though you don't realize that's sort of what's happening. Oh, and if you're into streams, you can do that whole thing in streams style as well if you want. But we'll ignore that for now. Now, once I've got something that's a pure function, then I can automatically apply memoization. Again, if you're in a purely functional, if you're in Haskell or somewhere, these sorts of memoization optimizations can just be happening automatically. In Groovy, we let you call .memoize on a closure, and that'll decide whether the optimization happens or not. And there's a few different variants. There's memoize at most, memoize at least, memoize between, and you basically get a cache that can shrink and grow with soft references and things. So in this case here, we've got a long word with 18 characters, and we're going to find the uppercase version of them all, and then do some calculations on things. Basically, the long story short is that without memoization, it'll take 18. I've got how many characters in there? Is it 18? Oh, okay. Of these numbers, I changed. Yeah, these actually reflect if you slept for 1 second, because I didn't update these numbers when I updated the value because I was showing people live and it was taking too long. So I halved the time here, but I didn't halve the numbers down here. Doesn't matter. It'll take, if I slept for 1 second, it would take 18 seconds without the memoize. If I just put .memoize on, I don't need to change any other code. It takes 7 seconds, right? So you can get that automatic functions here. What do you think will happen if you put memoize on math.random? Your degree of randomness might decrease slightly. Yeah. You'll get the same value back every time. Yep. So don't do it. Dice.throw, coin.toss. Unless you're going to win you can use this dice.throw to, and you need it to always, you're creating a craps game or something and you're going to be the winner, then memoize might be a good thing if you can get the right numbers on there, but otherwise don't do it. Okay, you can do it for there's a memoized annotation, so you can do this on methods as well as closures. We won't go into there. Memoize in the future. Who's faced that problem? Clear the cache, just clear the cache. Okay, the next pillar that we want to talk about is immutability. So if we have immutable data structures everywhere, it's going to allow us to have referential transparency. Right, all those some of those ugly examples we saw just won't be in play, and it's going to be very easy to reason about. And there's so parallelism and memoization, all those sorts of things are in play. Just a little bit on style. I actually probably don't need to go into this sort of detail. I often give people suggestions on style they should have in their code. Basically, this one up the top's doing a lot of mutating style things. There's ways to write things even in normal Groovy code without using any fancy functional libraries that might give me lots of benefits. Just with normal Groovy style, there's ways to do things that are going to not have mutation everywhere. And there's a bunch of methods that mutate in all the Java collections libraries, and there's usually nice alternatives where you can avoid that. We'll skip over that because I'm going to come back and look at that in more detail with persistent collections. Yeah, we'll have a whole slide on persistent collections. So I'll come back and talk about that. Has anyone read the rules for writing immutable classes in Java? Most of you would recite this before you go to bed each night, the list of 18 things or whatever you need to do to write your immutable classes in Java. Well, you need to do quite a bit of code. You need to do getters, but no setters. You need to have final backing, private stores for your variables. You need to have equals and hash code methods. You need to, there's a bunch of stuff you need to do. Groovy would kind of say a lot of that's boilerplate, so just do things like this. So that's the kind of thing that you can use in Groovy to get yourself some immutable classes, and I'd encourage you to be doing that sort of thing. So let's look at so immutable there, that'll work for your own domain classes, but you still want to have collections of these things, and you've got various options. So I want to talk about mutable, immutable, and persistent. Some of you this will be stuff you already know, but some of you may not be aware of it, so I'll just spend a couple of minutes on it, and then we'll move on. If you've got an array list in Java and you've got a couple of characters fed into your list and you want to add another character, it'll just mutate the list, okay? There are some algorithms, some scenarios where that might be the appropriate thing to do. It won't assist you with achieving pure functions or reference integrity. So if that's what you're trying to achieve, it might not be the way to go. You've had other options. So there's immutable collection types of various kinds. And in that scenario, what you would have done, what you would do is, I've got on a list with 2 strings in it. If I want to append another string, I don't actually touch the original list. In fact, create a brand new list and put the string value in there, and that's what I return. What that means is if people are still looking at the old thing, they can still point at this old thing, and anyone who wants to see the new thing can see the new thing, and they won't actually change. So again, there's certain algorithms when this is a fairly efficient thing to do, and it might be the way to go. It can lead to lots of copying of data everywhere. So for some algorithms, this will be not the ideal way to go. So there's a third style, which is called persistent data structures. And persistence here has nothing to do with the database. It's just that the data structures stay around all the time. So here, if I've got C and A as 2 characters, they'll be in a sort of linked list. If I want to add T, then I can just add it in and I can point to T here. Okay. So this turns out there's quite a large number of algorithms where this becomes a very efficient thing to do. So I'd encourage you to look at that as something that you might want to do. But don't assume that it'll solve all your problems. Let's just have a look at what it would look like. So here I've got pets. I've got 3 pets, a cat, a dog, and a horse. I'm going to go buy a goldfish. I'll have pets pointing to the old list, and so now I can create a new pets with the fish there as well. I've now got 4 pets in the new pets list. Anyone who's looking at the old list will see it. and they won't need to see any difference. They'll still see their list of 3. I've got now, anyone who wants to see the new list will have they'll be looking at new pets and they'll see all 4, but I haven't had to duplicate the information, right? So that's kind of looks like I'm getting the best of both worlds. And in many scenarios you are, but just be aware that not all algorithms will necessarily be efficient with this kind of data structure either. So if I go new pets and I'm going to remove the horse now, I've sold that off to someone who wasn't winning me any races. What's actually going to happen here? Well, it'll actually create a new list. So now I'll have pets, which is the original 3, and it stays there. It's persistent. It's always going to be there. I've got new pets, which is all 4. That stays there. And now remaining will actually be a new list with 3 things in it, and I will, at this point, have to copy. Okay? So there will be certain algorithms that you do that will be inefficient with persistent lists. And the good news is there is lots of research going on in this space to try to make these more and more efficient. So over time, we'll have ways to do many of these operations in reasonably efficient time as well. Okay? And this applies to trees and this sort of structure as well. So when you manipulate a tree, you have a modified version that's sort of half of the old tree and a bit of a new tree, and it'll have to potentially copy quite a few bits across, and you'll get these sorts of data structures. And so you'll see all sorts of finger trees, red-black trees, all sorts of different ones that actually have different performance characteristics in different scenarios. So they're things to bear in mind. If you want to play with some of these, there's a few nice libraries around. So VAVR, that's Java upside down if you stand the right way, sort of, because you couldn't use Java in the name of your libraries. P collections, Baguro, I'm not sure if I think that's the right pronunciation. So there's a few different ones around. There's a thing called functional Java, and there's actually a library on top called functional Groovy, which gives you a whole range of different things, monads and all sorts of things. So if you want to use persistent data structures, you've got a few options there. So just keep that in mind. So yeah, you can see here multi-way trees, rows trees, zippers, all sorts of things that are there. Okay. So it's all well and good to be able to balance one of these trees, but we're going to change the requirements as you go as well. So there we go. Okay, streams is a section I want to kind of skim over because I won't get to the next lot of slides if I spend... actually, no, lazy. I'm doing lazy first. I will quickly look at lazy. There's quite a few things in Groovy and even in Java where lazy is in play that you might not realize. So if you do a Boolean expression, then you've got short-circuiting happening. So that's a form of lazy evaluation that you've had in Java since the beginning of Java. So that's lazy evaluation. If you're using G-strings, the Groovy interpolated strings, and you put the little brace on here, that'll actually be a lazily evaluated expression that happens whenever you print out the string. Okay, so the first one will be evaluated when the string is declared. So that'll be the date when you run the when you actually declared that variable. The second one will be lazy. So it'll be when you print the thing out. If you've used XML slurper, then that's lazy evaluation of an XML file. So if you go and parse an XML document with XML slurper, and you do find all, and you've got some expression, and then you do find all with another expression, and then find all with another expression, you might think you're building up, I've got another list, now I've got a shorter list with my new constraint, and then a shorter list with my new constraint. In fact, nothing has been processed at this point, not until you actually go and evaluate something in the final list. At that point, it triggers evaluation, and it'll lazily work out all the things. It's got a nested set of closures that get executed when you do that. So lazy evaluation is something that's there. If you've used data sets, again, that's lazy evaluation. So I'm doing athletes, find all the ones that are after P in the alphabet, find all the ones that are born after pick the date, now sort them by date of birth, now reverse that list, At that point, the database hasn't been hit. So you might think, I've gone and either hit the database and got everything or whatever, but no, nothing's hit the database yet. It's not until you actually try to do something, it'll do a single query to the database with all of your constraints in there. Now, there's several libraries that do this now. Again, this has been in Groovy since sort of day dot. If you want to do this sort of stuff in your own code, if you're creating singletons, there's a lazy flag for that. There's a lazy annotation as well that you can put on, and it handles a whole bunch of different use cases, and it basically will do best practice Java idioms, but in Groovy, obviously, for handling the lazy evaluation. So double check blocking and all those sorts of things. It depends if it's a static method or not. There's a bunch of other libraries around as well. We'll skip over that. And you can look at some of those. Now, the streams is the stuff that I wanted to go and skip over. There's some streams are sort of fairly... I'd typically recommend you use Java 8 streams these days rather than any of the streaming libraries that have been around for a while. Yep. Okay. Recursion and then advanced abstractions, 9 minutes. We'll see how we go. So recursion, it's getting back to declarative versus iterative. So rather than trying to tell the compiler, here's how you should solve this problem, iterate this next, do this next, do this next. What you basically are kind of saying is, well, no, I'm not going to tell you how to solve the problem, but I can tell you how to break this problem into two smaller problems. And you try to tell it just that and nothing else. And if you can do that, you can have a recursive solution. You all would have seen that before. So factorial of n is n times factorial n minus 1. And you'd write it like that. Okay, just a little trick for Groovy. When I'm declaring a closure, if I have the closure over here, it hasn't finished defining it yet, so it won't see this. So just a tiny little trick. You either just leave the def off, and then it becomes, well, you can, yeah, there's a couple of different ways. I can just declare it first, and now I can just reference it. Okay, even though this hasn't been defined, it's been declared so it knows where it is. Or I can just use this little call trick. So I said a closure's got, we have a shorthand syntax. Well, if you can just use call, and that's basically call myself, so which happens to be me. So you can do a couple of those tricks, but that's kind of something we don't want to spend too long on. So that's factorial. This is subject to Stack Overflow, which the same thing happens in Java. There's nothing magical here. But what you would typically do is rework what this looks like. And this is kind of one of the smells of functional programming. Instead of writing it the way a human would understand solve the problem, you go and twist it around in such a way that it's now in a form that the computer can optimize it, or a human can optimize it. So here we've changed the original factorial to instead of just being n times factorial n minus 1, we've now got a little accumulator, and we pass both n and the accumulator in each time, and we iterate around here. The nice thing about this particular style is that it's what's called amenable to tail recursion, so it's a tail recursive function. That just means that if I go back, you can see here, when I go, as I'm walking down the list, I've got to kind of, on the stack, I've got to remember all the things that came before me and keep remembering all of those, and then I do my next calculation. And then once I've got to remember more and more things as I go down, and then I percolate my way back up. If you move it to the tail recursive style, you don't have that anymore. And basically, the compiler can optimize that into a for loop underneath the covers for you. Yep. In theory, this is. So the Groovy compiler doesn't do this automatically. So this one here is still subject to Stack Overflow, but we know it's amenable to tail recursive optimizations. We use a thing called .trampoline to invoke this mechanism. Okay. If we put .trampoline on it, now the compiler will optimize it. Okay, or it'll complain that it couldn't if it can't see that it's a one that's amenable to this sort of style. Now, there's a little bit of details on here, which I won't go into, but to cut a long story short, you end up calling, you call trampoline when you're declaring your function. So instead of wherever you would have had factorial before, you now got do factorial.trampoline, and then that gives you something that's you need to do a dot call on, but it turns out you can just do dot trampoline on. And this is so you end up with two calls to dot trampoline, which looks a little strange when you first see it, but once you understand what's happening, it makes perfect sense. So this is the syntax for how you would do it. And you can, there's obviously mutual recursive versions of that as well. And there's a version to put on your methods as well as closures. So keep that one in mind. Okay. There you go. Okay. Last section. So there's actually two examples in here. I'm probably going to just focus on the first one of these. So this is a little word splitting problem. The second example is a little monad type problem. I'll show you the cartoon for the second one. You can go look at the code for the second one in your own time. But I'm happy I'll be around for the rest of the conference. Come and talk to me if you want to see that example in more detail. So let's look at this one last example, and that'll be finished. So this is the Fortress code version to solve a problem for counting the number of words in a chunk of text that might be on a disk or something. So we might have a huge file, database of some kind with a whole bunch of ASCII characters in that file, and I want to count the number of words. So what I'd like to, I can do it sequentially, obviously, but what I might want to do is have some sort of parallel processing happening. You know, I might have a farm of computers that I can do this on. So what I want to do is split that big chunk up into sections, and I'm going to farm these out to the different compute processes in my farm, and see what results I get back. So first of all, this is just the sequential one, and that's fine. But now I want to do it. This is how the sequential one works. So it's basically it's doing a character at a time and seeing whether it hits a space. And if it hits a space, that's a new word boundary. Otherwise, it keeps counting the current word. And how do I parallelize this? Well, I can't, because it needs to know whether the previous character was a space at any point in time. So you might think, oh, we're kind of stuck. We've got this problem. If I go and split this up, and I've given this piece to someone, how can they decide how many words are here? So this might be the start of a new word, and then I've got two words, or it could be zero. Do I count this as 0 words because it could be that this could be joined on and this could be joined on, or what do I do? And it might look as if there's absolutely no way we can parallelize this. But what you do is you twist the problem around. And this is something I've suggested that you would want to do in functional programming a lot of the time. This is just one context in which you might do it. So we'll twist the problem around, and instead what we'll do is we'll remember some boundary condition on the left, we'll remember some boundary condition on the right, and then we'll count up all the stuff in the middle. So we've changed the algorithm. And once you move it around to this, then you can start doing it in parallel. And we'll basically put things into chunks and segments and so on. So you can see here we've got a boundary here, a boundary here, and we've boundary here, and we've collected all the words in the middle. So we do that in each piece, and then we have a combining operator that kind of puts our segments together. So if we've got one segment like this, we've done two that are side by side, then what I can do is I can add that number of words and that number of words together. I can join this bit and this bit, and then recalculate that bit as one word or not. And then I've got a bigger chunk, right? Makes sense? And then I can just go all the way down in that sort of style. So this is a map filter reduce style problem. And just by twisting things around, we can now do this in parallel. And what we've actually done here is created something called a monoid. So it's basically where you've got associative operators. So I can concatenate two segments in this case. I've got a plus on segment. I can concatenate those, and I can do it in any order, and I'll always get the same result. And I've also got a identity element of some kind. So I can plug that in either end of my algorithm, and it won't affect what the result can be. So if I've got those two things, I can now do it in parallel. And the advantage of that is that I can now do this whole thing in various concurrent styles. There's some different examples here that show how to do this in using actors and data flow and fork join and all sorts of things. But the fact that I've gone and put it into a monoid style algorithm is the thing that gave me that. The next example takes it one step further and shows a bit of monadic style. I won't go into the details, you can read it, but we all know the most famous monad is the monad Lisa. There we go. Just ask Leonardo. Okay, well that's all I wanted to talk about today. You can go and the whole slide deck and the whole all the code for this is on GitHub and Speaker Deck respectively, so you can go and look anything up, and by all means chat to me or shoot me a note if you have any other questions. Okay, thank you.